So can I do the thing where I make a comment and then ask a question? The comment is about the fraction of the mantle that is equilibrating with metal. So the impactor's core is only one source of metal that is equilibrating with the mantle after a giant impact. You have a lot of debris from accretion that's been hitting the planet since it last had a full-scale magma ocean that is sitting around at the mantle, and when the mantle melts, that is a significant, well-distributed source of metal that is going to equilibrate with the mantle around it. And also, the experimentally determined sort of dispersion of cores does not really capture the complicated dynamics of what is happening to the core in a lot of impacts, in terms of part of it does probably penetrate straight through, but often the cores are sheared.
This includes the shearing, this includes the emulsification.
That's but what I'm saying is that the core actually is, part of it merges, but part of it is actually, for example, in the canonical moon-forming impact, you have part of the core of the impactor's core which is added to the target's core during the initial impact, and then part of it is separated again and comes back and re-hits. So there are many more processes happening even to the impactor's core than just a simple emulsification.
Certainly, this is a simple model, and of course, if you have multiple pieces of core coming down on multiple locations of the Earth, basically you repeat this. Of course, smaller pieces will have a smaller cone. So the point is that we are very far from explaining through that process the depletion that has to be more than 2 orders of magnitude of highly cyclophile elements from the lunar mantle.
But what I'm arguing is that there are physical mechanisms why you'd expect most, like, this is key to your argument, that the inefficient equilibration of impactor, or not so much impactor's core, but if inefficient equilibration of the target's mantle with metal, wherever that metal has come from, in the impact is key to building up large highly cyclophile element and sulfur concentrations in the mantle. Whereas if you have more efficient equilibration, not necessarily a larger metal fraction, but a larger mantle fraction equilibrating through smaller pieces, whatever, then you return to the classical image of...
Absolutely. If one is able to bring a more efficient equilibration with the mantle close to 100%, then the problem goes away, and you can come back to the classical model without having to invoke the highly cyclophile element, the iron sulfide role. That's for sure. The point is it really realistic to expect that 100% of the mantle interacts with the iron core? So we need specific simulations to show that. And remember that the tungsten isotopes, the value of tungsten 182 to 184, in order to be reproduced in the terrestrial planet simulations, requires that the equilibration fraction is never unity. So it has to be substantially less than unity, otherwise you will get.
So my recollection may be incomplete, but K, which is the fraction of the impactor's core that equilibrates, has to be less than unity. But I believe that in most simulations they assume that H, i.e. the fraction of mantle, is unity. I may have misremembered that, but that is my assumption.
That K measures the amount of equilibration of the projectile core with the projectile mantle.
Yeah.
So assuming that there is no more than the mantle, that the projectile's mantle equivalent that equilibrates with the projectile core. It's never assumed it's the full mantle of the Earth.
I will need to check, but I think I disagree. But I will check before I ask. And can I ask my question, which I've now forgotten? So when you have the sulfur content of the moon, you said that you assumed that it was equal to the mantle of the Earth at the time that you separated the two. So I didn't quite.
Simplicity, yeah.
Oh no, of course I didn't quite understand the plot, because I was sort of just thinking of the interesting part about sort of what happens if you have a lower sulfur concentration. So can you explain this plot again? I didn't quite.
So this is the sulfur concentration in what remains in the mantle liquid, in the old mantle, in the magma ocean. So as the magma ocean becomes more thinner and thinner, of course the concentration goes up because all the sulfur is in the magma. And there are 4 curves depending on 4 initial sulfur concentrations, and that range from 300 ppm to 900 ppm, 300 being this one and 900 being this one, and then well, you go up. So it always goes up. So if you start with a very low sulfur concentration, basically you dissolve later when the magma ocean is thinner and thinner. And of course, at some point you run out of sulfur to sequester all your highly hydrophile elements. Now, I know where you want to come, that probably the moon does not accrete exactly the same amount of sulfur than the Earth because the sulfur is more volatile and so on. We just assume the gross chemical equilibration, but yeah, sure.
No, I was more, what is so you have here the sulfur saturation line in the red line.
Yes, yes.
How is that related to the volume percent crystallized axis?
Yeah, as you see, it changes with the volume crystallized. So first it goes up because the SCSS increases with decreasing pressure. And as the magma ocean becomes shallower and shallower, the basal pressure decreases, so SCSS goes up. And then you have a drop, and this is, don't really understand that comes from Lindy. That's because its chemistry of this residual melt is changing. But even if it were a sort of a horizontal acid, it would still dissolve at some point.
Okay.
All right, thank you, Mark. We move on with the next session, next talk for this morning's session. It's by Dr. Ian Garrick-Bethel from the University of California, Santa Cruz. So Ian is research interests are in lunar geology and geophysics, and is particularly interested in understanding the origins of lunar magnetism. And this is precisely the subject of his talk today. We're very happy to have been joined by the class in planetary geology students in the geology department. So hope you enjoyed the lecture and that you'll have plenty of questions for our visitor.
I think I need an adapter for the.
You need an adapter. I think it's this should one, this one.
Thank you. Right. Thank you. Oh, all right. Seems to work. All right. Thank you for inviting me here. It's been a great visit so far. So after talking to the microphone, because it's linked to the web, is that how that works? Okay. Okay. So yeah, thank you very much for inviting me. So I'm going to talk about the lunar magnetic field. And so today, the moon has no global magnetic field like the Earth. So you can't use your compass the same way you would on the Earth. But the record that we have, the geologic record, shows us that a long time ago, the moon almost certainly had a dynamo field like that of the Earth. And so I'll be talking about the puzzles that are, first I'll talk about the evidence that we have that there was a dynamo on the moon. Then I'll talk about the puzzles that are presented by that evidence. And I'll present some ideas about how we might make progress on that, including improved remote sensing data analysis, and even looking at the isotopic record of lunar samples. So anyway, let's start with some introduction. So the problem of lunar magnetism is really a problem of looking at the rock record. So the moon has no dynamo now, but it had a magnetic field billions of years ago. And so we are stuck looking at the records of that magnetic field frozen into rocks that cooled in that dynamo field. And so here, this is one Apollo 11 sample that has been studied and shown to be magnetized, and it's a fairly pristine sample. And the other way we can do this is not, we don't have to just look at rocks, but we've flown spacecraft around the moon, and we've found patches of the crust that are very highly magnetized, and we call these crustal magnetic anomalies. This is a spacecraft here from 1998 called Lunar Prospector that mapped out the global crustal anomalies on the moon. So this record in the rock allows us to make inferences about what was happening in the core and how a dynamo could have been generated. I also want to say that this record is limited, and this is even generous, I would say. We're probably talking 200, 300 million years after accretion of the moon. That is where our record of magnetism starts. And that's because we don't have pristine, very old samples. And we can only really work with pristine samples because there are other samples that have been beat up by impacts, and that tends to reset the magnetization. So that's one problem with working in rock magnetism, is that the rocks can be easily reset. And so a lot of the information about the formation of the moon, which has been one theme in this workshop, is not exactly accessible at this point. So this is significantly after accretion. But I will talk later about the history of the dynamo in the context of the formation of the moon. Okay, anyway, more broadly, I just want to say that magnetic fields are everywhere in our universe. They're generated in the sun. You can find them at neutron stars. You can find them in planets like Jupiter and the Earth, so extremely different planets, but they both have magnetic fields. And in planets, the dynamo, and so those planets that have global scale magnetic fields, there is this thing called a dynamo, and it's essentially the motion of an electrically conducting fluid, and it's producing a magnetic field. And so just to amplify that point, here's a picture, it's all from Wikipedia, it seems to be shown in a lot of places. What is a dynamo? So in the simplest view of a dynamo, requires a liquid medium of sufficient electrical conductivity. So in this case, liquid iron for the Earth's core. And I think it's important to say that the fact that your magnets are made out of like iron, and iron is ferromagnetic, is a total coincidence. And so when I learned that long ago that that's not related to the Earth's magnetism, I thought that was interesting. You can essentially, what I'm saying is, you can replace the Earth's liquid iron with any electrical, well, not any electrical conductor, but like liquid copper, for example, may well work just as well as liquid iron. And then on top of that, in the crudest sense, you need to cool that liquid medium. And when you pull energy out of that liquid core, you drive convection, and the convective motion is what allows the dynamo to operate. So that's a very simple view of the dynamo, and I'll come back to this later on. I thought this, there's also one theme in this workshop is the history of science, and I think this is an interesting history of dynamo theory. So in 1919, Lamore suggests dynamo may be responsible for solar and Earth's magnetic fields. And then in the 1920s, quantum mechanics was developed. But then, it wasn't until 1946 that people really came to accept the theory of how the Earth's field was generated. And even in the 1920s, Einstein had his own ideas that were wrong about how the dynamo was generated. So I think it's just interesting that the ideas about the dynamo came fairly late, actually, compared to some other fields in science. Okay, so I want to say that they're pretty important. So for planetary scientists, why do we care about dynamos? Here's a figure that I've been showing for a while that shows the Earth, Mars, Ganymede, Mercury, Moon, asteroids. And some of these objects have magnetic fields today, like the Earth, Ganymede, and Mercury, and other ones like Mars, Moon, and asteroids, they have no magnetic fields, but they once did in the past. And, what a dynamo is telling us, it's telling us about the internal conditions inside those planets. In order for an asteroid to generate a dynamo, then very special conditions are required inside the core, and the rate of energy transport across the core, and the chemical nature of that core. So if you find meteorites that imply that an asteroid had a dynamo on it, you're learning something about the interior conditions of that object. And that's just a basic interest of planetary scientists. Okay, so let's look at the moon's dynamo, the moon's extinct dynamo. Again, that does not have one today. And so what's interesting about it? So I'm going to show you that its field strength at the surface may have been very strong, and that is hard to explain because the core is very far from the surface. The core is very small, and the field should have been very small at the surface. But the field strengths we infer are quite large. And another fun thing, just for basic dynamo theory, is that the dynamo may have been driven in a way that's unlike any other dynamo we know of right now, and that it may be that the tidal forces were stirring up motion in the core and driving the dynamo in that manner. So it's a very exotic type of dynamo. We'll return to that. And as I said, the simplest view is that the cooling of the core is driving convection and driving the dynamo. So if you learn about the dynamo history, you're learning about how the moon cooled. And if you look at the moon at night, you can see that there's all these volcanic plains on the near side. So certainly the moon has undergone episodes of heating, and we may be able to learn something about that in connection with the dynamo history. And there's another concept called true polar wander, which is basically how the moon's orientation essentially has changed in time. Like if you look at the moon, it's possible that it was rotated 30 degrees to the west, and you would see a different face of the moon. That's basically a crude description of this process called true polar wander. And depending on the rock record of magnetism that we see, we may be able to back out where the one plate planet of the moon, how it was oriented in the past, using the unique information of the direction of the field frozen into the rock. Okay, so that's the background of why we care about the moon dynamo. And so I'll show you now some where we have come since the late 1950s in thinking about the moon's magnetic field. That's a little bit of review of lunar magnetism. So here's where lunar magnetism does fit into understanding the accretion of the moon. And if you go back, when people used to think that maybe the moon was just a big, cold meteorite, and this idea was advanced kind of overlapping a little bit with the Apollo era, but mostly before the Apollo era. That, on the left, you had someone, Harold Urey, who thought that the moon was this cold meteorite, essentially. And then other people thought maybe that the moon had melted, and the melting was extensive enough that the moon would form a core and be more like the Earth. And so those were two very different views of the moon. And of course, the hot moon idea turned out to be true, and that led to the giant impact theory that we believe is correct for the formation of the moon now. And so here's the first clues that the moon was either cold or hot came from the first mission to the moon. And these first Soviet missions that flew past the moon, these were flyby missions, they didn't have any cameras on them, but interestingly enough, they had some radiation sensors and they had magnetometers. Magnetometer is a very cheap instrument to fly, and it's a very fundamental geophysical measurement that has been made for over 100 years. And so they found that the moon has no global scale magnetic field. And the inference was maybe the moon had no core, and the moon was basically a cold meteorite. So that supported the cold moon hypothesis. But then, in the next 10 years, we brought back samples from the moon and found that they are magnetized. So you can see this cute little cartoon of the rock is magnetized. And this implied that this rock had cooled in a dynamo field, and maybe there was a dynamo in the past. And so here's just to get everyone on the familiar with this concept. I mean, a rock is basically sitting there in this magnetic field, and it cools down and it acquires a magnetization vector in the same direction as the ambient field usually. And so okay, so who cares about the formation of the moon? But this is saying that you need a core in order to have a dynamo, in order to magnetize a rock. So this supports the idea that the moon had a core in the past, and this supported the idea that the moon was hot. and then that's where we've been ever since. And so there is some, you do get something about accretion into the moon from the dynamo, but it's pretty basic. It's just very kind of crude at that level. Core. Okay, so then there's another way you can look at the rock record of magnetism, and it's from space, it's from orbit. And so here's on the upper left corner. So you can see here, this is a cartoon, or I guess a drawing of the Apollo mission module released this little sub-satellite, and it flew around the moon for a few months, and it measured magnetic fields, and it made the map you see here of the magnetic field. So this is like 170 degrees longitude, negative 10 degrees south, so this is the far side of the moon. And you can see that these contours here show that there's one area of the crust that is coherently magnetized. And the numbers are the magnetic field observed by the spacecraft in units of nanotesla. And you can see it's 12 here. And it turns out that the magnetic field we're all sitting in today from the Earth is something like 50,000 nanotesla. And this is 12 nanotesla. That's the field from the crust. This little blob of magnetized rock. So this is a very weak field compared to the strength of the field we're sitting in now. But it certainly is a coherent magnetization showing that the crust was magnetized. And then the other, maybe the last thing I want to say about the crustal record of magnetism is that we had put surface magnetometers down and were able to measure fields of the order of 100 nanotesla on the surface, again suggesting that the rocks were magnetized. Okay, so we have laboratory measurements and we have remote sensing measurements of the magnetized crust of the moon. Okay, so what magnetized them? So everyone at the time still didn't buy this, that the moon could have had a dynamo. People, again, were just getting over the idea that the moon had a core in the Apollo era. And then it was another leap to understand, can you have a dynamo on the moon? So people came up with very creative other ways to explain these magnetized rocks. Maybe some of you already have thought of them. We mostly ruled these out by now. And one that's commonly brought up is maybe the moon was really close to the Earth, or was close enough to the Earth that the fields in the Earth were magnetizing the moon. But it turns out that the strongest component of the field, the Earth, the dipole component, drops off like 1 over r cubed. And so by, at Earth, at the distance of the moon, the field is way too weak to produce the magnetism we see. And then the other idea was that solar wind fields could have done this. So the solar wind carries with it a field frozen into it. And those are also significantly too weak to have magnetized the moon. The solar wind, for the general audience, permeates the solar system. And as it's emitted from the sun, it's a mixture of plasma and frozen in that field. The other idea, if you look at the moon, what do you see? You see craters, and so many people, and still to this day, there's still ideas that somehow cratering was producing magnetic fields that were producing shock waves that would pass through the rock, and maybe some plasma was generated simultaneously from the impact that produced a magnetic field that was captured by the shocking of the rock. And it's a pretty involved process. It's a very inefficient way to magnetize a rock, but on top of that, it's also too fast. Any fields that come from plasmas tend to be short-lived, but these rocks have cooled over long time scales, and so they recorded long-lived fields, and that's one of the key constraints on the origins of these fields. So we've ruled these out. Of course, every year or so, it's fun to just take some time to think about any other new ideas about what may have produced magnetic fields on the moon. And I would love greatly to come up with an idea that doesn't require a dynamo, because it would be exciting and it would get over some of the problems we have with magnetizing rocks with a dynamo. Okay, so now I'm gonna tell you how when I say it's too weak, what do I mean? I mean, how do we know what the field was at the time? That's a big problem, okay? Because you have these rocks, and it's a pretty abstract measurement. I mean, geochemistry, you can measure. You're measuring a property of the rock, but it's not a vector quantity. I mean, like the magnetization of rock could be multiple magnetization vectors on the rock. So it's like at magnitude and direction. And on top of that, the rock may not record fields very well. It might just be a poor recorder. So it's a difficult measurement to go from this rock you have and take its magnetization vector and figure out what the ancient field was on the moon. And there's like a whole body of work that was dedicated to doing exactly that, figuring out, going from rock magnetization to ancient field on the moon. And that's how these arguments were made when I say this is too weak. And I'll show you now the strength of the field that we think it did exist on the moon. And I have this one equation that kind of permeates the rest of the talk, and it's basically relating the magnetization of the rock, okay, which you measure in the lab, to the strength of the magnetizing paleo field. And essentially, it's just a constant of some efficiency factor that depends on the rock's ferromagnetic properties. The more iron, crudely, the more iron the rock has, the more efficient and strongly magnetized it will become. And so you need to calibrate that out, because you don't know if the field was really strong in the past and the rock has very little iron, or the other way around, maybe it has a lot of iron and the field is weak. And so those two trade off with one another. And so decades of work, and this was all revisited in decades of work after Apollo, plus another revisiting of all this work in the last decade, since maybe 2008, 2009, has put together this plot here that shows the paleo field strength on the ancient moons. That's the surface field you would see on the moon from that dynamo. And I'm using the units here, but maybe no one notices. But that's, okay, so the y-axis is the paleo field strength, and then the x-axis is the rock sample age. So these are all rocks that we have from the moon, and this is the strength of the field. And here's the modern Earth field. So you can see that at some point, the moon's magnetic field was getting up to Earth strength, okay? And it's basically the solar wind field would be not even visible on this plot. And the Earth's magnetic field will not be visible either. So we know that the ambient magnetic field of the moon is very strong, and it is approaching Earth strength values. Okay, and so we don't think it's solar wind field. We don't think it's the Earth field, but this is a problem to explain from a theory perspective. And you can see that very easily by understanding that, I drew the Earth core a little bit, but the numbers are correct. Essentially the moon's core is so far from the surface, and the rapid rate of decay of the dipole component of the field, like 1/r cubed, means that for the moon, you're talking, if everything else was the same and the moon was generating a dynamo just like the Earth, you should have a field that's at least 10 times weaker than the moon. You shouldn't have a field that's equal to the Earth strength field. Okay, so it's very hard to explain these Earth strength fields. So that's a big puzzle. But people have put more work into this, more detailed work, and try to use so-called scaling relationships to figure out what is the maximum field I would expect from theory on the moon. And this is work based on a review paper, Weiss and Tiku, but also more recently, a paper by Alex Evans and others last year. And so this line shows you that, if you assume generous parameters in the scaling relationships and took the energy budget of the moon and allowed the moon to just cool over time, you would expect maximum fields in the order of 5 microtesla. And here we are at 50 microtesla and more. I mean, up to 100 microtesla is what we see from the rock record. So, but you can also play some more extreme games. Like you can take the entire energy budget of the moon and dump it into the core in a certain very short window of time, and that gets you up to maybe on the order of 10 microtesla for a very short time. And so it's ultimately really difficult to explain some of these very strong fields that we see from a theory perspective based on scaling laws. Okay, and so that has motivated an entire set of work to explain what kind of dynamo is this that could possibly generate these fields. And so there's been ideas about traditional convection dynamos, and some of these ideas were just to explain at all how you can get a dynamo period. They didn't even talk about the strength of the field. But like I said, like the regular cooling of the moon, thermal convection is the first thing listed there. There's also ideas of getting the timing right. So, you know, one thing I didn't talk about enough is that there's this brief period when the field is very high. So, you know, why is it that the field was strong for such a short window and then seems to have died off? So that's another puzzle. So there's ideas of basically allowing cooling mechanisms to be delayed on the core that eventually would pull heat out of the core at a later time, and that would actually drive vigorous convection. There is a way people have ideas of putting water in the lunar mantle to get the heat pulled out of the core faster or over longer periods of time through convection. Thermochemical convection is another way. Basically, as material crystallizes at the core mantle boundary, latent heat is released and drive convection that way. So there's the very crystallization of the inner core can help drive your convection. And then I think this is an interesting paper that shows you kind of the desperation of the field right now, is that this is a solution that says that maybe there was a dynamo in liquid rock that was on top of the core. And it's very difficult to get the electrical conductivity of liquid rock high enough to make this kind of dynamo, but people are desperate to figure out a way to make the moon's core larger, and if you had a liquid layer of rock on top, that would help you. And then another class, and this is maybe for a theorist, this is maybe the most interesting part, is that you have dynamos that aren't driven by temperature alone, but they actually are stirred dynamos. So in a dynamo, the basic concept is you have some electrical current, and the electrical current eventually will dissipate because of the resistivity of the conductor. And so you need to put energy into the system to have that current continually flowing. And one way to put energy into the system is just take the system and just stir it up mechanically. You can imagine like stirring up a can of paint. But, you know, and how could you do that in the moon? And it turns out there are ways of stirring up the liquid core in the moon, and that has led to this whole idea of mechanically stirred dynamos. And these series of papers here and other ones that I've left out have come up with some fairly interesting models of that. And these maybe can get us the fields we need, but we don't even know because the simulations we're still learning about these types of dynamos. This is a brand new type of dynamo being studied by the community. And even the most recent paper on it shows that it doesn't really work. So this is like our big hope in some ways to explain the strength of the lunar magnetic field, but it doesn't even work in the most sophisticated scenarios. But they left out some nuances of the problem. So maybe it works. This is like a new frontier in modeling this type of dynamo. Okay, so then the other thing to think about is maybe that all these measurements are not exactly, we shouldn't be relying on them. Maybe these are not perfectly accurate measurements of the strength of the field on the moon. I mean, you can see the community has put a lot of emphasis on them, and they're coming up with new models of dynamos based entirely on this crazy high magnetic field you see on the moon. So one, thing I am going to talk about now is that I advocate for doing adding a whole new set of measurements of the ancient field of the moon and using this map here to do that. So this is a map of crustal magnetic anomalies on the moon measured by two different spacecraft, actually. The Japanese sent a spacecraft and measured magnetic fields. And all of these patches of crust are very strongly magnetized. And so, just like we use the rocks in the lab to figure out the strength of the ancient field of the moon, very little work, almost none, has been used, and no work has been done to figure out how strong the magnetic field of the moon was from all of these patches of very magnetic rock. And so this is a map measured at 30 kilometers altitude by the US and Japanese spacecraft. So these are called crustal magnetic anomalies, and I advocate that we can start to use these to figure out how strong the ancient field was, and that would give us a totally independent record from the rock record that has been motivating all of these dynamo theories. And the nice thing is that these are automatically screened for us to be the strongest magnetic anomalies. These are, like, by definition, the most magnetic things on the moon. So if you really want to test, if there was a strong dynamo, these are great places to go, because the altitude is already attenuated to weak anomalies out. And so, okay, why didn't anyone do this before? I think people, first of all, didn't really think there was a dynamo on the moon. There was a long time when people thought it was all impacts and exotic processes. So now that the community's moved towards acceptance that these are cooled in a dynamo field, maybe now we can start to use them to learn something about the dynamo. And so I would say, no serious efforts has used them for paleo intensity estimation so far. Okay, so let's look at these anomalies in a little more detail. And so what are they? What are they made out of, actually? And we don't even know what they are. That's another problem, and that's why no one has probably done this yet, is that we don't know if the material comes from within the moon or was deposited from outside the moon. There's no topography, although I'll show some places where we have discovered some topography, but the community to this point there's no correlation in the topography with these magnetic anomalies. So they're invisible to us, what's actually happening beneath the surface. But they are highly ferromagnetic, we know that. So here's two broad theories of what actually is happening here. And the first one is that there's an asteroid, it hits the moon, it makes a crater, and it sprays some material, maybe iron-rich material from the impactor onto the surface. And that's exogenous origin, something from outside the moon. Another idea is that this was intruded volcanic material, and that's from internal to the moon, and this indigenous materials. And then, there's some magnetic field, and everything cools in the magnetic field, and then you're left with the magnetic anomaly you see today after the moon's field's gone. Okay, so can you get the paleo field strength, the ancient field of the surface of the moon, from these magnetic crustal anomalies? The problem is there's more challenges than the laboratory analysis. Laboratory analysis, you can always do so much more with a lab sample than remote sensing, and we're going to see that right now. And so we want to get this, and we're stuck with this from remote sensing. We don't have lab samples of these special places on the crust of the moon. So I'll show you how that's difficult. And then the other problem is we have no idea what the thing's even made out of. So that's another problem, maybe, that we don't know what these materials are. That efficiency factor depends on the ferromagnetic properties of the rock, and we don't even know what these things are made out of. Okay, so first I'm going to show you how we can get around those problems and maybe estimate what the paleo field strength of the moon was. And so let's first look at what M really is. M is the density of magnetization. It's the moment, the magnetic moment divided by volume. So you take your current carrying wire, okay, and you put it in a box, and the volume of your box is the denominator, and the moment in the current carrying loop is the numerator. So it's the density of how that little magnetic moment is spread out for the volume of rock. Okay, so the total moment of a magnetic anomaly can be estimated fairly well. So you take some spacecraft measurements of the magnetic field, and there's some red anomaly that you see there, and you can figure out reasonably accurately what the moment is. It basically looks like a dipole from far away, and you figure how strong that dipole is. But the problem is you don't know the volume of the rock unit, and that's a major challenge here, because the volume could be either of these two options here, and it would make a very similar field. So you can see that if the volume was this versus that, you don't actually know what the volume is from high up. So you can have two magnetic bodies with the same moments, different volumes. They're going to have different densities of their magnetization, and they're each producing indistinguishable fields at the spacecraft altitude. And this is a problem, a very common problem in geophysics inversions for sources, like in gravity. Like you don't know if you fly along, you measure an increase in gravity in the ground. Is that due to some small body of lead, or is it due to some larger body that's a little bit denser? So there's a trade-off here between volume. Okay. The other problem, that's one problem. And the other problem is you don't know what this material is made out of, so you don't know if it's a strong dynamo or the rock was just extremely good at recording the field. So yeah, with a lab sample, you can figure out this efficiency factor chi, but it's not possible remotely. So what do? Okay, so first I'm going to show you a 2012 paper illustrates the horrible nature of this problem. And if imagine you have a magnetic anomaly and the spacecraft measures a 10 nanotesla perturbation in the field locally, this shows you here, what goes into making that 10 nanotesla anomaly. Imagine you have some rock unit of some thickness. The color gives you the thickness of the rock unit. And these are the different values of chi that are allowed in this plot. And these are the different paleo field intensities that I want, the ancient field on the moon that are allowed. And you can see how these are all free parameters. And any of the colored areas here are solutions that give you the 10 nanotesla anomaly you see. We don't know how thick the unit is. We don't know what it's made out of. And all of those are dependent on the ancient field strength. So it's very challenging in that regard, because we don't really want to get, again, the paleo intensity of the ancient moon's field. Okay, so my solution is to at least make one assumption, and the assumption is that chi is the value for the most magnetic materials we know of in nature. So I'm just going to assume an extreme value of chi, and it turns out to be 2 in these units. And that value is found in iron meteorites and a special classes of meteorites like C4 chondrites. And these are extremely magnetic materials. And there's a compilation in the paper referenced there that goes through maybe at least 3 dozen or so types of material. And so if you assume that this material that we're seeing is the most magnetic material there is, we can set chi to its maximum. And that gives you the minimum dynamo field. If the rock was less efficient, then the ancient field of the moon must have been even stronger to produce a given M. So that's the first thing we're going to do. We're going to fix this to the maximum. And then you can make this kind of plot where you say, well, if I find some crustal magnetization M here, I can have this minimum dynamo field. Okay, the field must have been this strong at the y-axis, because this line assumes that this is the most magnetic material you can find in nature. Now you could argue, well, maybe there's something else out there we don't know about, and maybe that's what these anomalies are. And I concede that may be true. Of course, that would be a discovery on its own. But setting that aside, so this would be the minimum field we would infer if we measured some rock magnetization M from remote sensing. So if you found some rock magnetization with 10, say, you would infer that the ancient field of the moon is 5 microtesla. Okay, now here you can see the actual estimates people have made for lunar magnetic anomalies. And this is, the state of the field is in very poor health because the anomaly estimates span multiple orders of magnitude. So we have no idea from these current estimates of what to say about the dynamo field. Okay, but first I want to break this into separate sections. And the separate sections here are regions of field strength that are explainable and not explainable with current theory. And so down here, you can see that these regions of the plot, here, if you found some rock magnetization of like 2, and you found that the ancient field, the minimum field is something like 3 microtesla, that's not a big problem for theory. But when you start to get into this yellow region, you're making special pleading cases for what's going on in the core. And then when you get over here into this region, this is very difficult to explain with any existing scaling theory for how dynamos operate. So this simple way to break the problem up into three regions is what I've done. And so then the question is, can you figure out the rock magnetization M? And is that possible with any kind of precision better than the precision you see at the top, which spans multiple orders of magnitude? Okay, so next thing, can we get a high constraint on M? And it actually would be cool to find one that's high as well, that would support the rock record from the sample. And so what we really want is a well-constrained volume, as I've argued. And it turns out there's this one type of anomaly on the moon, which I think is really special, and I think any geologist out there will find these features fascinating. And they're called swirls. And I think that swirls, which I'll explain what they are, swirls are a place where we can probably constrain the volume of the source, the magnetized rock. And these places are also where the magnetization on the moon is likely strongest, at swirls. So what are swirls? Here is a map of the magnetic field contours on the moon, centered on the near side. And two famous swirls are called Reiner Gamma and Gerasimovich. And I'll talk about Reiner Gamma magnetic anomaly and swirl. So swirls, what are they? They're places where the magnetic field of the crust is so strong that the plasma from the solar wind cannot reach the surface. It's like a little miniature magnetosphere. And the easiest way to understand that is to look at this plot of incoming solar wind ions. And the solar wind ions get deflected away from areas where the fields are perpendicular to their path from the Lorentz force. And so what happens is the solar wind protons are coming in, and they're getting deflected depending on the morphology of the field. So yes, as it says, solar wind is not significantly deflected along vertical fields, but horizontal fields tend to deflect the solar wind. And what that does is, it turns out the solar wind darkens the surface, making dark areas where the protons are hitting, and where there's no protons hitting, the surface is bright and fresh looking. So here's a place where we think that's happening. This is a map of the field with the contours at nanotesla at 20 kilometers. You can see a scale bar there of 30 kilometers, horizontal scale. And you can see this strange feature is this color pattern that is very crudely associated with this increase in the magnetic field. And there's no correlation at fine scales here. But you can see there's a lot of color change at very fine scales. And so what I'm going to propose is that we can use these fine scales in the color change as an ultra high resolution magnetometer, essentially. And so what we think is happening here is that these bright regions are the places where the horizontal fields are strong and the solar wind plasma is blocked from the surface. And then the dark areas, like I showed you in the previous slide, are these vertical regions where there's cusps in the field and the solar wind plasma can leak in and darken the surface. And so, and I think that is a much higher resolution inference than that is available to me alone from the map of the field contours. So it is an assumption that I will make. And these brightness markings can be used as a high resolution field map. Okay, so I'm going to now try to make an argument that we can estimate the volume with precision, with decent precision of the source body that is producing the magnetic field. Okay, so a ton of studies have actually looked at the magnetization vector for this region, and they've all reported the same thing. With very small errors. So we think we know that this thing is magnetized in the page and to the west a little bit. And so that these vectors here are representing the magnetization direction of the rock. And so we noticed another thing is that this is an extremely symmetric feature. I mean, there's no other feature quite like this on the moon that is so elliptical and symmetric like that. And it's basically an ellipse, and it fits an ellipse extremely well. And that level of symmetry puzzled my student and I, Megan Kelly, on this paper that we wrote on this. And so I was thinking, what could really, okay, it looks like a disk, but it turns out that if you magnetize a perfectly elliptical disk, it's homogeneous, then you end up getting these fringe fields at the edges of the disk that would be vertical, and that's what I wanted. I wanted vertical fields at the edge of the disk. So you can remember, yeah, that is where I want vertical fields at these cusp features, okay? And so a magnetized disk will actually have, magnetized in that direction, will have fringe fields. Let's get to the next slide. So here we take a disk and magnetize it in that direction. And those are the cusp features where we think plasma is reaching the surface. And here's a map of the field at 2 kilometers altitude from a magnetized disk. And you can see it has these circumferential cusp regions, exactly like you expect from fringe fields coming off of the disk. Okay, and so this, this seemed like a reasonable model for the source body, is an elliptical magnetized disk. It's not perfect, and you can play with some of the, you can make the disk a little thicker at its edges to get the cusps to wrap all the way around. But this, I think, gets us a long way in explaining the high amount of symmetry in this feature. Okay, so then you can think, well, okay, how do you make an elliptical magnetized disk? And it turns out that it's actually not that hard on the moon, because there's a lot of elliptical landforms, a lot of elliptical geologic forms on the moon, and those are impact craters. And so you can find oblique impact craters and regular circular craters, of course, but oblique impact craters are highly elliptical, and they have the requisite symmetry as this proposed magnetized disk. So the idea is that a crater formed, a crater, and this is a Mars example. This is an example of Mars, but I'm proposing this would happen on the moon, and that crater's melt sheet could have been elliptical, as you would expect, and then become magnetized, and then that whole region was buried by flood basalt. So what's its volume? And that's what I keep telling you. Is like, I want to get the volume of this thing, get a good constraint on M. And these semi-axes can be determined by matching where the cusps are, and so we can know that pretty accurately within 20%, which is fantastic. And then the thickness becomes a real key here. And the great thing about craters, I would say, in geology, or for us, is that people study craters a lot, and they've studied them on the Earth, they've drilled into them on the Earth, they have estimates of the thickness of the melt sheets at craters, numerous craters on Earth, and even for the craters that are of the appropriate size for this feature. And so if you look at the appropriately sized similar features on Earth, you can find drill estimates of the melt sheet thickness, and you can scale it to our crater, and you get something like a couple hundred meters of melt thickness here. And here's an example of one of those Earth craters that was used as an analog for this crater. Until you get 160 meters. And if you use that for the magnetization, you get something like 70 amps per meter, which is a huge magnetization, actually. And so, like, some of the strongest magnetic anomalies people talk about on Mars are in the order of tens of amps per meter. This is the most magnetic feature on the moon, so maybe it's not surprising that you get such a strong bulk magnetization in the rock. So what does that mean then for the strength of the dynamo? If you take this plot that I introduced to you, and you put our swirl point on here, 66, it puts us in the region that is very, in the so-called high field region that we learned about from looking at the Apollo samples. And it puts us in the region that is difficult to explain with theory. You get about 40 microteslas as the minimum field. And you can conclude that maybe the high field epoch that is difficult to explain is real, those high fields we see from the Apollo samples, they may actually be real, and we should rely on them. Okay, and so that's just one data point, and so now I'm going to show you where else we could do this on the moon with remote sensing, and a couple other ideas about the future. Okay, so the thing is, getting that 160 meter thickness for the melt sheet is, you can do a lot better than that, because the numerical modeling people are doing of impact craters is incredible now. So I'll show you that with some improved impact modeling, we can get the melt volume exactly for this crater. Instead of scaling into Earth craters, we can just run a bunch of simulations that produce the same width and the same semi-axes for this feature and see what the melt volume really is. And it's actually probably less than 160 meters, which makes the magnetization even stronger. So, but I don't know the answer, but this is a very easy to do next step. Way easier than getting a sample, for example, of this feature. And we'd also like to know how much iron material is retained by the impactor, because that is what presumably is causing the magnetization to be so strong at this feature. Okay, so there's that as a future direction, but there's also, we've discovered other places that are correlated with topography. And again, if you correlate magnetization with topography, you can get the volume, you can estimate M, the magnetization, the moment density. So here's a map of the magnetic field made by my student, helped me with this, Rachel Maxwell, and she has produced this map, and you can see there's two blobs of magnetization at 20 kilometers altitude, and about 60 kilometers is the horizontal scale here. And we noticed that these blobs of magnetization are very correlated, especially the southern half, with these crater fill deposits. And this is, to our knowledge, the first discovery of any correlation of topography with magnetization on the moon. And so because of that, we think that we can continue our work to estimate with decent precision the volume of this magnetized rock unit and estimate M. So that remains the work that we will continue on. The other idea is, this is totally a new idea that I thought I would throw out here. And this is an idea called isotopic magnetometer. So this is a totally different thing now. So, okay, that was the end of the talk about the work I've done on magnetic anomalies. And I'm just going to wrap up with this idea that there was a long time ago, there was a paleomagnetosphere on the moon. Not surprisingly, okay, if you had a magnetic field on the moon, it's going to, maybe there's something just interacting with the solar wind. So you can see this simulation that we've done recently that shows what we think the ancient solar wind density was and its speed, and we slam it into the moon, and lo and behold, not surprisingly, you create a magnetosphere. And it turns out, Mercury, you could have learned this from Mercury. Mercury has a very weak dynamo field relative to the Earth, but it still has a magnetosphere that blocks the solar wind. But we were able to simulate this for what we think the moon. This is a 2 microtesla field. So remember, the Earth's field is 50 microtesla. This is a fraction of what we think the moon's field was. So yeah, the solar wind, what does it say? Simulations show weak fields can block the solar wind. Now here's a paradox I want to propose that I think needs to be resolved. And it's that you can find soil breccias that are very old, on the moon, billions of years old, and they are loaded with implanted solar wind species. And everything, this is saying that the solar wind should not be reaching the surface at all for very weak fields, but yet we have rocks through all of lunar history that have implanted solar wind plasma species in them. So there's ways around that, but I do think this needs to be studied more. And one way we're doing that is by we're simulating whether or not heavy species will penetrate the magnetic field, while the lighter species like helium, maybe and hydrogen stay behind. And so, is there isotopic fractionation in the solar wind implanted isotopes in the Apollo record? So I think this is one route. Basically, it's a combination of sample analysis, looking at the isotopes in samples and comparing that to simulations. And because there should be somewhere out there, if there really is a magnetic field on the moon that was strong, there should be a soil breccia that's 4 billion years old or 3 billion years old that has no solar wind implanted species in it. But then actually it also gets difficult to date the breccia because the dating methods are based on the amount of solar wind and planted species. Anyway, we can talk more about that if you're interested afterwards, but I think this is an area that deserves some future thought. And then finally, I just finished proposing a new space mission with the Jet Propulsion Laboratory, and that goes into a pool of mission concepts that NASA is considering and won't pick a finalist for at least another 18 months. But this is a mission to improve our knowledge of the rock magnetization M. So here's again that diagram, and you don't know the volume of the source body. Okay, that's the problem. These two different volumes can give you basically the same field altitude here. But what if you had low altitude data? And it turns out low altitude data would help you. If you're right at the surface, these two different features would look different in low altitude data. And so we came up with this concept to send spacecraft at like less than a kilometer above the moon's surface. So there's no atmosphere on the moon, so you can make science measurements in orbit at like 500 meters. A meter, you can be a meter above the surface orbiting the moon and be making science measurements. And our knowledge of the gravity field of the moon permits this now, so that we can come down very low and make extremely low skimming trajectories through these magnetic anomalies. And this concept is called nanoswarm, and we proposed it in July. And it's a fleet. It sends a whole fleet of these probes. They're based on CubeSat technologies, actually, which maybe you're familiar with. And we've picked out 5 prime targets where we think are the most interesting on the moon. And we basically hurl these probes into this, basically the hearts of these features. And we make a bunch of plasma measurements as well, but we measure the magnetic field at extremely high cadence. Basically, it's kind of like flying a helicopter over through these features to measure with high resolution the structure of the field to infer the volume of the rock that's magnetized. Okay, so the conclusions are rock samples. They tell us that the lunar magnetic field was inexplicably strong. And I have been advocating that we can start to think about, at least, paleofield estimation and crustal magnetic anomalies. It's not totally hopeless under some sets of assumptions. And preliminary analysis at the Reiner Gamma swirl suggests that really the field may really have been as high as the Apollo samples tell us. So I advocate further modeling efforts to follow up on that work. I think simulations of the paleomagnetosphere and further thought about soil branches could help us. And of course, new measurements in space at extremely low altitudes would help us get that precious M value, which leads us to the paleofield stuff. Okay, thanks. To some questions.
Time for questions? Yes? Didn't ask any questions.
So I have 2, and so this swirl analysis is extremely interesting. So the first one you showed, so the one of the ellipse you proposed,
Yeah.
you showed that there is actually no correlation between the magnetic field lines and the topography, right? There was an image before.
Certainly not the topography.
Yeah,
I mean,
and so shouldn't you expect that you have field lines correlated with the ellipse if this was an elliptic structure of magnetized material?
Okay, the thing is, all of our measurements are inconvenient altitudes. They're at the altitude where the anomaly just looks like a dipole. And so I may have it in the extra slides, but I can tell you briefly that you can take a magnetized ellipse and a whole bunch of other small anomalies, and then you upward continue the field to the spacecraft altitude, and it just looks, the whole thing becomes a dipole, and you lose all of the information. So an elliptical magnetized disk is actually consistent with the field map here. It's all self-consistent, yeah.
And the other issue is that this, if I understood well, is in a Mare structure. So it's
Yeah,
relatively young. So the first plot you showed, the super magnetic field, ended at 3.6 billion years ago.
Right.
But if this is a impact crater in a Mare structure, it's fairly young. right?
Well,
So
it's
that would
very-
suggest that the magnetic field lasted longer than previously.
Okay, well, the oldest Mare here is 3.3. So, and it's like buried in that Mare. And so, we have another paper where we argue that the crater, based on some superposition arguments, that this whole unit formed in basalt. So it probably formed between 3.9 and 3.3, which was the main pulse of volcanism. And so we think this, yeah, those are the most likely age, 3.9 and 3.3, and that does overlap with the high field there.
So a key question, of course, is the susceptibility. And you pointed out that it's hard to know this by remote sensing, and perhaps it's even hard to get it if you have a rock in the lab, because you don't know whether the susceptibility at the time you acquired the magnetization is the same as what you get now when you do your demagnetization experiment. So my question is, to what extent can we be helped by lab experiments and theory? Theory tells us, of course, that typically rocks have a much lower susceptibility, and therefore you might infer a larger field than the real field, simply because of the domain size and the grain size and the fact that the domains are all not lined up and so forth. This is stuff I learned from Joe Kirschling.
Yeah.
Because he's fond of saying that these tiny domains that we sometimes see in biological systems are particularly suitable for getting magnetic field. We see that in bacteria. So I guess I'm asking, if somebody says they see a certain magnetization and they know the geometry, can you infer an even lower field than what you called the minimum from theoretical arguments about domain size? And can you test those ideas by looking at the mineralization of the material in the lab?
Yeah, I thought a little bit about this. I mean, I guess I would favor a very empirical approach to studying the the susceptibility of the most magnetic materials we have with heating experiments in controlled atmospheres. So most of the rock, the samples we have studied do not have this extremely high susceptibility value. And so if we, go get those samples and heat them in the lab and cool them in a field and try to improve the precision that we measure that chi, the inferred chi, that is what I would advocate to look, more carefully at those materials from an experimental perspective.
Presumably there's no theoretical problem, right? That is to say, if you said, hypothetically, that the magnetic field of the moon never got even remotely as large as the numbers you were showing, that in reality, they were 10 or even 100 times smaller, and therefore the susceptibility was 10 or 100 times larger.
Yeah.
That doesn't violate any fundamental physical principle. There must be some fundamental principle.
Yes, there is a fundamental
But there's
physical
a
principle.
huge range that's possible.
Yeah, okay, so you can construct a rock that has a susceptibility that is certainly higher than the one we see in nature. And so there is a theoretical limit, and you could definitely do that. And it's just a question of which extreme assumption do you want to make. Do you want to assume that these materials are unlike anything we've ever seen before, which is maybe true, I don't know, it may be true, but yeah, there are physical limits, I guess, I will say, yeah, I do agree with you.
This is a question probably for Dave rather than you. But
Okay.
You can answer it. So the only physical mechanism dynamo mechanism you can think of is a precession dynamo. Could you explain that?
I kind of left that. I mean, yeah, Dave has more insight into this,
So
but
I was wondering what updates are there to that theory since the last 15 years?
the way I framed it was like this is the last man standing. Like there's no the other theories don't work. The new frontier could get us there, but Doesn't have, it may not at the end.
You're not advocating.
I'm definitely not advocating.
It's a possibility.
It's a possibility, but maybe Dave, yeah.
I'm not going to advocate it, but I will point out that Sabina Stanley has looked at this and she's very smart at figuring out how these dynamos might work. And I'm not sure whether it's published, but it might do better than Uli Christensen scaling, which would be desirable. Still seems unlikely though, that you would get to these extremely high fields. The precession dynamo does have an attractive aspect to it because it might violate the scaling, which is normally based on buoyancy flux. Mechanical mixing, if it works at all, and you pointed out that some people doubt that, but if it works at all, it might violate the standard scaling, but we don't really know.
Woman over here had a question.
Okay, thank you, Ian, for the interesting talk. The surface area to volume ratio of the moon is large relative to that of the Earth.
Surface area,
The surface area divided by the volume ratio of the moon, also planet Mars, planet
Okay.
Mercury, are larger than that of the Earth.
well, I mean, yeah, it's like,
So also
Okay.
the rotation period of the moon is longer than the rotation period of the Earth.
yeah, well, it's a
Do you
month.
think that these two factors can play a role in reducing the strength of the magnetic field of the moon?
I mean, it's dominantly the small size of the core, and it's so far from the rocks are forming at the surface, and the core is just far away. So that really hurts you a lot. I mean, the surface area to volume ratio comes into like how quickly the object cooled,
Yeah.
and so yeah, that could play into the duration of the dynamo, or I guess maybe the strength under certain special kind of conditions, but. It's more duration, I would think, for the surface area to volume ratio, the duration of the dynamo, but it's just so difficult because the core is so far away. The core is so tiny on the moon. That's really hurting you a lot.
Planet Venus is more or less similar to the Earth in terms of its size,
Yes,
but even though it has no magnetic field also.
yes.
So I think perhaps in that case, the rotation period of planet Venus is the main role for the absence of a planetary magnetic field.
People, I mean, again, this is Dave can have has a lot of insight into this, I'm sure, but you know, the rotation probably isn't the main issue. I mean, that's stopping Venus from having a magnetic field. It's the probably just there's no heat flux coming out of the core that's driving convection that can support the dynamo. So yeah, I don't know if you want to say something about the role of rotation. I mean, I feel like you've thought about, obviously you've thought about it a lot, but
Yeah. Anyway, these different arguments need further research, I think, to see what are the actual reasons that are responsible for a planetary magnetic field.
definitely, yeah, I mean,
Yeah.
you have to compare the planets to understand, of course.
Hi, so I have two questions. The first one is very interesting to me as a biology major, is
Okay.
the fact that you can see from the Paleo field, 4 billion years ago, we have that spurge in the magnetic field of almost 100 microtesla, right?
Yeah,
And because this is the same time, almost, we hypothesized that life emerged on Earth.
yeah.
Do you think there's an association between that spurge in the magnetic field of the moon and the emergence of life on Earth?
Yeah, it's an interesting question. I will say there's maybe some connections, and it's that first of all, we don't have rocks from the Earth that are really old, like past 4 billion years. So it's like hard to really know when life started, just because the record is not that old. But I mean, you know, there's people have argued that there was this bombardment at 3.9 4 billion years ago. Maybe that set some limit on life taking place on the Earth. Can you link that somehow to what we're seeing in the magnetic field of the moon? There's ideas that those large impacts hitting the moon could have broken the moon out of synchronous rotation, and then the subsequent rocking motion of the moon would cause a dynamo. So there's creative ways to make those connections. I mean, I guess in my mind, I think that the onset of when life started, it's so difficult because of the poor rock record we have, and at that time, not only the rock record limited, but then the life record is even more limited. That pushing back that far. Interesting question.
I have a very tiny technical question. When you measure the volume of the source, of the rock source, do you usually take into consideration like shadows from different angles to calculate it? Or it's not necessary?
Well, so the volume is entirely based on, I mean, at least for this example, so you're asking about the shadows in this optic, like, is that what you said, the shadows?
Yeah, the shadows of the rock source, not necessarily from the pictures, but usually they create, like, they produce shadows if it's that's really altered.
Okay, so this source is completely buried. So there's no, it's under probably at least a kilometer of basalt, volcanic basalt. I mean, and, for technical considerations, this picture was taken with the sun right behind you. So, so there's just going to be, it's just, we see no shadows in this picture, but even if you had a topographic map, you would not see any correlation of any, it doesn't show up at all. It's just a completely buried magnet. You take your refrigerator magnet and bury it in some sand at the beach, and that's what you're faced with.
Okay, one last question.
Thank you. One magnetic parameter that could also be of interest instead of the susceptibility would be the coercivity. Is there anything like this that's of interest here?
Yeah, I mean, all these properties are related. I mean, the way it's, I mean, in practice, you estimate the susceptibility by looking at the saturation magnetization, which is related to the coercivity. So, I mean, you can, in the lab, okay, so you're faced with a Apollo sample in the lab and you want to estimate its efficiency factor, the susceptibility. To do that, you can perform a series of experiments and through different relationships, estimate chi. And if you want to measure the coercivity of the rock, you could do that, and that could get you closer to figuring out chi. So it's plausible, Thank you.
Okay, please join me in thanking Ian again for.
Thank you for inviting me. Appreciate it.
So we'll break for lunch and we'll regroup here again at 2 p.m. for a session on dynamics.